This is Module 10, Equilibrium Skeleton Notes. We're going to start off with an introduction to equilibrium. In many chemical reactions, it is important to consider both the forward and reverse reactions. No matter what mix of products and reactants we start with, eventually the system settles at a constant ratio of products to reactants at a given temperature. Equilibrium occurs when the forward and reverse reactions occur at equal change with no net change in the concentration of products or reactants in a closed system. You still have forward and reverse reactions going on, but the net concentration is staying the same. Let's consider this diagram here with the reaction of 2NO2 forming N2O4. This is a one-step reaction, which means that the forward direction is an elementary step, the reverse direction is an elementary step, which becomes important later. If we were to write the equation for the forward rate equation, we would write rate forward equals Kf times NO2 squared. And there should be a little bracket in there that's missing. The reverse reaction rate equation would be rate reverse equals K to the reverse N2O4. So let's take a look at this diagram. We've got red representing our NO2 molecules, and this is time 0. We have a flask with just NO2 molecules in it. The reaction begins to proceed to produce N2O4. And so eventually we form N2O4 molecules, fair proportion of them, until we reach a state where the net concentration is constant. Notice that rate forward is equal to rate reverse. If instead we were to start with just completely N2O4 molecules, again, we would reach the identical equilibrium position. So this is graphic. Now let's take a look, or particulate level. Now let's take a look at a graph. So this is the same reaction. This time I've just written the equilibrium going in reverse. It doesn't matter which way we write it because it is an equilibrium. So now consider starting with a flask filled only with the N2O4. So here we are with just the N2O4. So at this point, the N2O4 disappears. And we're seeing that NO2 forms. As we look at what happens to the formation of NO2, initially the reaction is very fast. We have a steep slope, and then the reaction gets slower. We see the slope getting more shallow. So the rate of the forward reaction slows. So rate forward slows. At any given time, the relative rate of the NO2 appearance is going to be twice that of the NO2 disappearance, simply based on the balanced equation. So N2O4, let's try that again, NO2 always appears twice as fast until we get to equilibrium. So we know that equilibrium has occurred when the concentrations are no longer changing. So from this point on the graph over, we have equilibria conditions. Now there is no net change in the concentrations. The concentrations are constant. Before equilibria, the concentrations are changing. In this entire region, we are going to use our little k because this region is kinetics. So everything before equilibria occurs is kinetics. That's what we were studying in the last module. Now we are on the right-hand side of the graph. We are going to be talking about equilibria. Our last question here is which compound is favored by the equilibrium, N2O4 or NO2? If we look at our graph, we have more of the NO2. So we would say that the NO2 is favored, or NO2 formation is favored. Now, bear in mind that this can change with temperature. So at the specific temperature that we are specifying, NO2 formation is favored. We're going to look at the graph in a little more depth. We said at equilibrium, rate forward equals rate backwards. And let's mark equilibrium again just so we know where that is. So everything on the right-hand side, once our concentrations are constant, is equilibrium. Everything on the other side is kinetics. So we've said that Kf, N2O4, rate forward, rate backwards are equal. Therefore, this equality holds true. What we're going to do is rearrange so that all of our constants are on the same side. And when we do that, we get K forward over K reverse, this is the kinetics constant, over NO2 squared over N2O4. And then when we do that, we can take these two, since they are both constants, and make them one big constant. K is the equilibrium constant. K depends on temperature. One of the ways I like to think about this for myself is K is like a baby, okay? The reaction has not grown up. We go to a big K because now we're at an adult, okay? The reaction has reached its steady state. It's not changing anymore on a net approach. So you can think of, your elementary school teacher probably taught you, you use baby Ks and big Ks, okay? So baby Ks are for kinetics, big Ks are for equilibrium. Let's take a look at the same equilibrium, and what I want you to look at is the relative concentrations of N2O4 to NO2, no matter where we start, okay? So again, chemical equilibrium to the right-hand side, kinetics to the left. So kinetics with a little k. If we are tracking what is going on with the N2O4, and let's color code these so that you can clearly see what's going on. We have N2O4, and now I'm going to highlight N2O4 in the other graph. And then we're going to use a different color also for NO2, nitrogen dioxide. Nitrogen dioxide. If we look at these two graphs, for graph A, only N2O4 is present initially. And we end up roughly with 0.03, well, it looks like 0.035 and 0.15 molar respectively of each of the species. So let me just go ahead and write this in. So we're going to say that this is roughly 0.35, 035, 0.035 molar, and this is roughly 0.015 molar. If we look on the other side, the concentrations are identical, 0.035 and roughly 0.015. So no matter where we start, we're going to end up with the same relative concentrations of products to reactants. That's why we have the equilibrium constant K. So let's go ahead and write that in there. All right, so we are done looking at graphs. You can complete my AP 10.1, Intro to Equilibrium, in Canvas.